Okay, so these are the goals of what we're going to cover. I mean, obviously we're not going to get through it all today, but we will get through some of it. All right, recording. Can everyone hear me? Beautiful. Good. Okay. All right. So here's what the definition of a rational expression is. Again, as I just said, it's a quotient of two polynomials. By definition, it's a quotient of two polynomials. Okay? So basically, you have one polynomial divided by another, right? So you have p of x over q of x. P of x and q of x are two polynomials. So just like I said before, right? You know, with integers, then you get rational numbers. Same idea. From the polynomials, you get rational expressions. And how do we get that? We divide. Form fractions, in other words. Okay. Now, here are just some examples, like 1 over x. That's a rational expression. Constants themselves are polynomials. We have 1 over x squared minus 1. We also have, x squared plus 4 over x to the 5th plus 3x to the 4 minus 2. All right, so these are just some, easy examples of rational expressions. Right, one polynomial over another. In fact, a polynomial, just like any integer itself, is a rational number. A polynomial itself is a rational expression. Mostly because if you divide by 1, you really don't change anything. So p of x for any polynomial, p of x over 1 is just p of x. Hence, any polynomial is itself a rational expression. Okay, now, one can also consider the domain of a rational expression. We saw what the domain was of a function. The domain we saw, I think, of equations, if I remember correctly. The domain of a rational expression, it's just all the numbers except those that make the denominator q of x, in this case, 0. So it's all the numbers such that the denominator is not 0, is another way of saying it. So basically, to get the domain, right, you would determine where the denominator is 0, and then the domain is everything else. We actually have done that before, I think, if I remember correctly. We did that a little bit in section 2.4. Not much of it, but we did a little bit of it. So let me say it again. The domain is all the numbers, all x, such that q of x is not 0. That's all. You don't want the denominator 0. Good. All right. So here's an example. Here's an example. Okay. So basically here we're going to find the domain of this. I mean, here it's a little bit easier because the denominator is already factored. Namely, actually, I forgot to say something. We're actually going to use stuff we've seen earlier to figure out the domain, because these are polynomials. We can factor, we can do synthetic division, as you'll see. And we can use, for instance, the quadratic formula. So those will come in here. Got to say that, but I just said it now. So again, here, the denominator is already factored. The numerator, we don't care about when we're finding the domain. Okay, so what did we do? Again, we set the denominator equal to 0. We solve that, and basically the domain is everything else. I mean, we solve this instead of solving the product not equal to 0, mostly because it's generally a lot easier to solve equality than an inequality. Okay, so from here, what do? Remember, you set each factor equal to 0. That's how you solve that kind of equation. Each factor, if you have a product equal to 0, you set each factor equal to 0 and solve. So we get x is 0, x minus 2 is 0, and x plus 3 is 0. We have 3 equations that we solve. Well, I guess really 2, because the first one's obvious, x equals 0. I mean, the only solution to that is 0. The second equation here, right, what do? We're going to add 2 to each side, right? Because we have x minus 2 is 0. We want to know what x is, so we add 2 to each side. Okay? Doing that, we get x on the left equals 2. So from here again, let me say it again. We add 2 to each side. Okay? Right, that kills off the minus 2, so we get x all alone on the left, x equals 2. Okay. Now, we have x plus 3 equal to 0, the last equation, right? So what do? We want to solve this for x. We subtract 3 from each side. So we get x, so we subtract 3, and we get x equals negative 3. So the solutions then to this equation, the solutions to these 3 equations are 0, 2, and negative 3. So the domain is all numbers except those. So the domain is all numbers except 0, 2, and negative 3. Now, you actually could write out that set using fancy notation. I know the book does it, but again, if you just wrote this on a quiz, test, or whatever with me, that's fine. I didn't go through all that fancy notation that the book does. And again, I'm only expecting you to know what I cover. So you could just write out in words, in other words. You could write out in words what the domain is. That's what I'm saying. Any questions on this? Okay. Here's another one. Again, we have this denominator, right? It's a quadratic. That is its degree 2. What I would do, again, unless I'm told otherwise, I would just solve using the quadratic formula. That is, to find the domain, right? We set the denominator equal to 0, right? That's what we do. And unless you're told what method to use, I would just use the quadratic formula. That's a lot easier. I mean, factoring has its advantages, but if all you care about it, but again, I'm not being told the factor, so I can just use the quadratic formula. So A is our leading coefficient, B is our coefficient of x, C is the constant. Here's the formula. Okay? So what do we get? -5 plus or minus square root of 5 squared minus 4 times 3 times 11. There is a plus here, I think, because originally there was a minus here, but I wanted it to be plus. So, over 2 times 3, which is this. Now notice under the square root we have a negative. The square root of a negative, right? That's not a real number. We know that. What does that tell us? This has no solutions. Right? You can't take the square root of a negative number is not a real number. We're only looking at real numbers here. So because of that, okay, the domain, so because of that, that this has no solutions, no real solutions, that is, and so the domain is all real numbers. I mean, I wrote that as an interval here, but again, you could just say the domain is all real numbers. So I hope that makes sense. Are there any questions about that? Okay, I'm not sure if we'll get the complex numbers, to be honest, but we'll see. All right. We just got the recording.